Hello and welcome to another class of ATMO 412. Today we're going to talk about baroclinic instability. And this follows a few classes in which we had sort of taken a more phenomenological approach. We talked about extratropical cyclones, we talked about atmospheric fronts, and these are all great, and we discuss what leads to the formation or the intensification of fronts, which we call frontogenesis or cyclogenesis. But even though we try to take an approach which was as theoretical as possible, we're still lacking some deeper understanding of the framework, the conceptual framework that is sort of underpinning these phenomena. And when we talk about baroclinic instability, the first question we want to ask is, what is an instability? What do we mean by instability? Although we have an understanding of what an instability is from our day-to-day life, in math, instabilities mean a very precise thing, a very specific thing. And they mean a situation in which small infinitesimal perturbations can grow spontaneously, okay? So an example from classical mechanics would be, if you put a ball at the very tip, if you manage to balance a ball at the very tip of a pencil, for example, it'll be really hard, but not impossible. In that case, any small perturbation to the ball, if you just touch it even slightly, it's going to make the ball fall down, okay? So that would be an example of an instability, perfectly unstable case. There are other cases that are more, we call them metastable, but we don't have to worry about such things for now. Examples of instability, well, there are many examples, of course. One example that is often observed are Kelvin-Helmholtz instabilities in the atmosphere, and these are generated by shear, and sometimes they give rise to clouds that have very beautiful shapes, and I encourage you to go and check it out. The baroclinic instability, so whenever we qualify it as baroclinic, we mean that the energy which is needed to grow the perturbation is not extracted from the kinetic energy of the background flow, but rather is extracted from the potential energy of the base state. Okay, we talked a little bit about this when we talked about the energetics of eddies in a few classes ago. So it's not really, it's not a kinetic, the transfer is not from the kinetic energy of the base state to the kinetic energy of the perturbation, but it's from the potential energy of the base state to the kinetic energy of the perturbation. Okay, and how is this discussion of baroclinic instability? How is it helpful in our current discussion? Well, it's helpful because we still had no precise understanding of why cyclones form, why upper level waves form. Okay, so if we take, for example, if we look at this figure here, we have two different waves, right? And what leads to the generation of these waves, and what makes the formation of cyclones possible? If you remember, we talked about cyclogenesis and the intensification of cyclones, and we said, well, assume that there's some vorticity here, and assume that there's an upper level, there's an upper level trough that is coming down. Then we talked about the stretching of the column and how that led to the intensification of vorticity, but it still doesn't explain to us why there should be an upper level trough, why should there be, or how can there be vorticity to begin with, okay? And in order to get a conceptual understanding of what is going on, we want to simplify our lives as much as we can. This is something that is done often in math. Why make your life complicated if it can just be easy, right? And so for the time being, we're gonna assume that the Earth is completely free of topography, and it only has one type of surface. Doesn't matter if it's an ocean or land, and what kind of land type, it doesn't matter. That is not going to play any role. And in that case, the atmosphere would likely develop a jet structure like our atmosphere. But then what's going to happen to those jets in this perfectly smooth planet that we're envisioning, right? Are there going to be waves? And if so, what is controlling the waves? Their amplitude, their wavelength, and so forth. And in order to answer this question, we're going to need some theoretical framework. Okay, and this is exactly how we're going to study the baroclinic instability. Now, we are particularly going to focus on a problem called the ED problem. And the ED problem is a way of conceptualizing the question that we have in mind, simplifying the theoretical framework, and then trying to address this framework, the question of instabilities within this framework. And this is called ED because it goes back to one of the first people who really addressed the question. And this was a guy, surname was Edie. And Edie and Charney were sort of the first ones to really study this question. People in the Bergen School of Meteorology that we talked about a few classes ago didn't really give a satisfactory understanding of why cyclones exist. They had this polar front theory, but it didn't really explain where things were coming from. Okay. And also, since we talked about fronts are shown to be and are known to be the result of a large-scale pattern, right? And they don't lead to the formation of the large-scale patterns. They're a response of something that happens, a response to the formation of the cyclone, but they're not the cause of the cyclone often, okay? Okay, so how do we go about for this ED problem? Look, let's not make our lives too complicated. And if you want to know exactly how the ED problem is written down and how it is solved, then I encourage all of you to check out the math on the textbook. Here we're just gonna sketch what we're gonna do. Okay, how this demonstration, how this proof goes about, so that we have some kind of understanding of what is needed in this case. So we're gonna start and we're gonna assume a Boussinesq approximation and an F-plane. Okay, F-plane means that the Coriolis parameter is held constant, and the Boussinesq approximation means that we're going to ignore density variations as long as they're not coupled to buoyancy. Okay? We're going to assume some kind of a basic state where we have some wind shear over here. So there's a background wind. The background wind is zonal, so there's no meridional, no vertical component. This is in response to some pressure gradient. This is a meridional pressure gradient, obviously. We're going to have some kind of a temperature profile, hydrostatic approximation, no funky latent heat releases for now. And we're just assuming that pressure and density are a function of latitude and height. So they're zonally symmetric, okay? It's a pretty restrictive picture, if you will, but it's a good starting point to try and understand what is going on. Also, I apologize for whatever reason. ED doesn't seem to be an accepted term. Let's see if this fixes it. I don't think I could go through an hour with seeing this red line here. Apologies for the autocorrect who doesn't know the word ED. But anyway, we're also assuming that the flow is adiabatic. There's no friction, as we said. Hydrostatic approximation, we're in an F-plane. We're assuming the Boussinesq approximation. And we're also going to assume that the flow is approximately geostrophic. So QG should hold. we are assuming a very simple boundary, and this boundary is bounded by rigid lids, both above and beyond. It's periodic in the longitudinal coordinate, and it's infinitely extended in the y direction. Remember, this is an F-plane, right? So we're assuming an infinite equator, in a sense. So it would be a bit like a cylindrical planet, okay? And if you assume all of these things, then you can write the equations of motion for the system equal to this over here, okay? These we've seen time and again, so we're not going to go through these equations once again. And this is the part where I would like to accelerate a little bit, and I don't want to spend too much time on the math, and I invite all of you to look at the math a bit more carefully if you're interested. And sorry, the red line here is, okay, well, we're just going to have to live with this. But anyway, let's assume for simplicity also that the basic state has some kind of a vertical shear. So let's assume that the shape is simple. And the vertical shear is nice because it then lets us write very simple thermal wind relations. Okay, so the vertical shear is like this, and it goes from 0 at z equals 0 to a certain value u when z equals h. Okay, so this is linearly growing from the surface. Not a great approximation, but also not a terrible one, particularly given that we're just trying to simplify things for now. Okay, the shear is independent of the latitudinal component here. Okay, so at any latitude, that's the shear that we're going to have. Because of the thermal wind relations, we can also write down the shape of buoyancy and also the geostrophic string function. Okay, and the buoyancy is going to be a function of latitude only, obviously modulus and parameters, and the string function is going to be a function of both height and latitude. Okay, from this you can see very easily that you can just rederive the UG by taking a y derivative. So easy peasy. All right, so we're going to separate all the variables into a basis state and some kind of a disturbance, okay? An eddy, if you will. And we can do some massaging of the equations, and we can show, first of all, that u prime g is 0 as a result of our assumptions. And the remaining equations for v prime g and u prime ag and for the buoyancy, the perturbation buoyancy, are these three equations. And also the QGPV is this equation, okay? And this better be conserved in this case. The equations that we wrote above can be solved, and to solve these, we're also going to need these relations, okay? So these two relations put essentially v prime and b prime in contact with phi prime, and so we can simplify things a little bit. And our strategy is that we're going to leverage this QGPV equation to get to some solution in a moment. What we want in the end is some kind of an equation and a solution for phi prime, so that we can understand what phi prime is gonna do. And once we have phi prime, that we can compute pretty much everything else. Okay. One interesting thing when we talk about the energetics of the system is that we can write down kinetic and potential energy that are associated with the disturbance that we're considering. We said earlier that it can be shown that u prime g is 0, and so the kinetic energy is simply v prime g squared, and the potential energy is just simply written like this. And it is possible to show that these two can be summed together, and the equation for the total energy, if you will, so the potential and the total energy is written as the sum of these three terms that are somewhat reminiscent of the energetics that we talked about when we discussed the QG approximation a few classes ago. And we have these terms that are conversion terms. This PAPE, this is a term that extracts potential energy from the basic state, from the basis state, and puts it, makes it available to the eddy that we're generating. And then we have another term that is converting this eddy potential energy into eddy kinetic energy, which is then going to generate the disturbance that we observe. So these are the terms that are most important. This is the Baroclinic term. Over here, if you remember in the QG part, we had discussed a very similar term to this, and we obtained these terms simply by integrating this equation over the entire x and z directions. Okay. So these are the source terms that are involved in the transfer of energy from the basis state all the way to the disturbance. And we're still going to have ageostrophic circulation, and the ageostrophic circulation looks very similar to the equation for the ageostrophic circulation looked very similar to the ageostrophic circulations that we discussed for the atmospheric front. So it is possible to write these in terms of both U prime AG, the zonal, the ageostrophic component of the zonal perturbation, and the vertical perturbation. We can write these as derived by a simple stream function. And from the equations that we wrote before, from the momentum equation and the thermal wind balance, it's possible to show that we can rewrite very simple equations for this stream function, very similar to QG equations. So second derivatives, let's say a Laplacian in the a 2D Laplacian in the xz direction, which are the directions that we're interested in, and a q vector that leads to that acts as a source term. So something very similar. And this is given essentially by the zonal derivative of the V of the meridional perturbation of the meridional wind, and the meridional derivative of the buoyancy. And it's easy to show that just from here and what we know about Laplacians and how we can interpret Laplacians as like minus the function, that that regions where this dv prime g dx is 0 are associated with stream function maxima. Okay, so back to the ED problem. We wrote down all the equations that we need, and again, check out all the steps on the textbook. We wrote down all the equations that we need. We figured out the energetics. What we want to do now is look for a solution through normal modes. What does that mean? What do we mean by this? This means essentially that we're going to assume that the function, the perturbation, is some sum of trigonometric functions, of waves, of certain frequencies and certain wavelengths. And if you remember Fourier analysis, that shouldn't come as a surprise that this makes sense, and it actually makes sense to do this analysis. And so let's assume that each function can be written as an infinite sum of sines and cosines, or complex exponentials, which is roughly pretty much the same thing. Now, let's plug a generic wave into this equation, and let's see how waves are going to respond to the perturbation. Essentially, are going to respond to the equations of motion, and let's see how if there are some waves that become unstable, okay, and what are the waves that become unstable faster than all the other ones, okay? And so in order to do this, we assume that the geostrophic function, phi prime, can be written as a wave, okay? So real part of a complex exponential. So this is essentially, we're assuming phi prime is a cosine, but we could have chosen the imaginary part, doesn't really matter. And, it would just be a shift in the phase over here. But, most importantly, in complex analysis, you don't need to even worry about this. You can just assume that this is a complex exponential, and that's what it is. Now, if, in this case, k is the wave number, and it is what it is, if this argument over here, k multiplying x minus ct, if this remains a real number, then this remains a complex exponential, meaning that the function phi prime is an oscillatory function, okay? It's going to be some kind of a wave, okay? And phi hat z is whatever shape we want. Whatever shape is going to be dictated by the equations. We don't care about it for now. But if we were able to show that there are times in which c over here takes complex values, so if c has an imaginary part, then the imaginary part with the imaginary part over here would lead to behaviors which are not oscillatory. And so in particular, this is minus I times, let's say there's another I. If the imaginary part over here is such that it produces a negative real part, then the solution phi prime just dies off to 0. But on the other hand, if this is imaginary, which gives another, with the imaginary unit here, it gives a real number, and we can show that the real number is positive, then this leads to an exponential growth. And so something that starts off as a small perturbation and becomes really, really big, which is exactly what we're after, okay? Now, the trick here is to leverage the conservation of PV, plug in this shape of phi prime, and then show that there exist cases in which C takes imaginary values. Now, if you do that, if you plug this back in and you do a little bit of algebra, and you're welcome to try, and it's recommended that you try, then C, you can show that it has this peculiar shape, where S is this strange non-dimensional function over here, okay? And this is an equation. Okay, so we have a square root. If the square root is negative, then we're good, right? Because square root of a negative, I am hallucinating. If the square root is positive, then all is good, and you can show that C has, that C is real, and it has some values that lead to an instability. And if you do a little bit of, this cannot be shown by analytical methods, but with a little bit of a graphical methods, you can show that there is a region in the phase space over here where this square root is positive, and C is a perfectly reasonable reasonable phase speed of the wave for which this phi prime grows. Okay, so over here in this region over here, then C has an imaginary part, and this leads to the exponential growth of the wave. Okay, and it also shows that there exists a value that we call as 0 over here, where it's like a cutoff, if you will. Okay, so there can be values for S that grows, but only to a certain point. After that, there's a hard cutoff here, and this corresponds roughly to a wavelength of about 2,500 kilometers in the mid-latitudes. Okay, so if you do that, then this is great. We found that there are cases in which the wave can grow exponentially. So it has an imaginary part, and so this wave begins to grow, and we can do a couple of things. The first thing is that there's ways to determine which mode has the greatest growth rate. And if you do that, you can find this Cmax as this function over here. And this is a configuration that has wave number 607 at 45 degrees latitude. Okay, so something similar to what we see in the real atmosphere. And we could also solve for phi. Okay, we can also find, we could plug it in and we can find the 5z. If you remember if we go back over here, we can find the phi z that we can determine from these equations. And if you then plug the function, so this is a somewhat complicated function that depends on these hyperbolic sines and cosines. And if you plug the solution of the string function over here, you put everything together, you put the wave, this exponential together with the phi function, then you have a string function that looks like this, that have maxima here and minima over here. And these two, the bottom and the top plot here, represent essentially this solution here, where we've taken apart the bottom component and the top component over here. Okay, so this is the solution of phi that comes out of this. And interestingly, notice that there is a phase shift, a tilt between the bottom and the top. Okay, so this is the string, what the geopotential would look like for this perturbation, and this is reminiscent of what we found when we discussed extratropical cyclones. That there was the low level circulation and the upper level of circulation. They were not perfectly stacked on top of each other, but there was a phase shift. Okay, so it's interesting that we found a theoretical framework to analyze this that reproduces some of the features that we knew were associated with these cyclones. And also notice that the shear is going in this direction, towards this direction, and this is leaning against the shear. This cyclone is tilted, leaning against the basic shear. Okay, and because everything, if you remember when we talked about the equations, everything could then be related to all the other functions could be related. Could be related to the geopotential. Then we can also compute the meridional geostrophic flow. We can compute the perturbation temperature, and we can also compute the vertical velocity. Okay, and notice that we find areas of first of all, this meridional geostrophic flow is pretty much in line with what we knew to be the stream function, and so this is reassuring, because that's what we would have expected from the geostrophic flow from the geopotential. And notice that the temperature has a strange, almost like a strange structure, because it's tilted in the other direction. Okay, and so this means that this area of there's an area of warm temperature that is associated with positive values of the string function, and at the low level, warm temperature is associated with flip sign of the string function, and something similar happens with the negative perturbation temperature. Okay, so this picture over here, you can show that it corresponds to a northerly heat flux, which is also great news, because these perturbations arise as a way to transport heat from the tropics to the poles. And so it's great that this is exactly doing what we'd expect it to do. So here, the result is that we have warm lower troughs and cold upper troughs, and vice versa for the ridges here. And also we have ascent in regions of warm air and descent in regions of cold air. Okay, so we have a nice upward heat flux from this solution. And it can be shown that the shift between the thermal and the stream function, there's about a 21 degree phase shift between these two. And this phase shift is consistent with the self-amplification mechanisms that we talked about a few classes ago. Okay, and it's important that these functions are sort of phase locked, because if you remember, when things were stacked up in the right way, then this could lead to the amplification of these waves. But in order for that to happen, we need the height scale to not be too small. Okay, so the other thing I wanted to mention is that one could play a game and ask, what is the function of the upper lid, if you will? And so if we remove the upper lid, what is going to happen? What if the atmosphere was infinitely tall? And you can show that in that case, we don't have instability anymore. Okay, and so if the troposphere was much, much higher, and this could be the case, for example, in the tropics, then you could show that the phase speed of the wave doesn't have imaginary part anymore. And what you'd end up having is that you just have oscillating waves that cannot amplify in these sort of structures that we discussed earlier. And the final thing I wanted to say is that what we're showing here is what you'd call a finite amplitude. Not a finite amplitude. This normal mode is almost like the opposite of what you'd have in a finite amplitude situation. Okay, so here we're considering very small perturbations and how these grow. Okay, so this would be the Lorentz effect with a butterfly causing typhoons. But this is not the only way in which disturbances can grow. There are so-called finite amplitude perturbations, and these are things that are due to, other conditions in the Earth. The Earth is complicated. Okay, so it could be like a result of mountain flows, or monsoons or breezes, what have you. There can be things that cause the generation of vorticity other than the spontaneous growth. Okay, and so it is still a question, I guess, of how much this normal mode analysis is relevant, given that there are so many finite amplitude perturbations available on Earth. But there are many cases in which the cyclones that we observe exhibit a structure that is very similar to an ED model, if you will. So it grows according to the ED growth rate that we had derived over here. So this ED growth rate over here. So I guess the point here is, let's continue to put this in context. So there can be instability, meaning that something grows from an infinitesimal perturbation of the atmosphere, and there are cases in which this can lead to the growth of large-scale perturbations, large-scale disturbances. But this is by no means the only way in which these disturbances can grow. There can be finite amplitude stuff that still lead to the formation and the intensification of these cyclones. Okay, so this is pretty much what I wanted to say. I didn't want to get too deep into the math because that's not really the point of this class, but I would invite everyone to take a look at the textbook and take a look at how the normal mode analysis is conducted, because this is, particularly if you're interested in the research aspect of this, this is how instabilities are often studied. So, you find a basis state and you do some kind of perturbation, and then typically people do normal mode analysis and try to find how different modes grow, find the mode that is growing fastest, and then they study this solution from this mode. Okay, so that was all. Thank you for listening, and I'll see you in the next lecture.